Welcome to Thought Frontier.
Welcome to a deep dive.
Oh, a deep dive.
Yeah, a deep dive into the mind-bending world of quantum entanglement.
Sounds exciting.
It is. It really is.
Well, I'm ready when you are.
Okay, so you've heard the buzz about quantum entanglement, right?
Yeah.
Two particles linked across any distance.
Right.
You change one.
And the other changes instantly?
Exactly. Even Einstein called it spooky action at a distance.
He did.
But today we're going to go beyond the hype.
Sounds good.
Can this really let us talk faster than light?
That's the big question, isn't it?
It is. It is.
I think we'll have some fun with that one.
Well, we've got some incredible research for this deep dive.
Oh, fill me in. What have we got?
We got cutting-edge research, historical context, even a peek into what NASA's up to these days.
Go NASA, huh? Always pushing the boundaries.
They are?
Well, I'm all ears.
Let's unpack this, shall we?
Let's do it.
So, what's really captivating about entanglement is that it might not just be some quirk.
Right.
It might be a fundamental rule of the universe.
Yeah. You know, that's what's really fascinating about entanglement. It might not just be a quirk, but a fundamental rule of how everything works.
Exactly. It's almost like the universe has this hidden network.
Yeah.
A connection that we're just beginning to understand.
Absolutely.
And to really get this, we need to go back to when even mentioning entanglement was risky for a scientist.
Oh, risky business. I like where this is going.
Oh, yeah, definitely.
Okay, so back in 1972, John Clauser, a Caltech alumnus, this guy, he really thought there was more to this spooky action than met the eye.
Wow.
Yeah, even if it meant risking his career.
So what did Clauser do that was so revolutionary?
Well, he designed an experiment to prove entanglement was real.
Okay.
He took two entangled particles, separated them, and measured one, the result. Measuring one immediately told him the state of the other.
Whoa.
It wasn't just theory, it was happening in a lab.
That's mind-boggling.
It is.
But hold on, doesn't this clash with, like, everything we know about the speed of light being the ultimate speed limit?
That's right.
Didn't Einstein have a problem with this?
He did. Einstein's theory of relativity. It's built on the idea that things can only be influenced by their immediate surroundings.
So, like...
Yeah, imagine kicking a ball. It's your foot that moves it, not something across the room.
Okay, yeah.
And, of course, cause must come before the effect.
Makes sense.
What?
So where does entanglement fit in? Does it break these rules?
It appears to. It really does. Entanglement suggests there's an instantaneous connection, communication happening faster than light. But here's where John Bell enters the scene with his famous theorem.
Bell's theorem. I've heard of it.
Right, you've probably heard of it.
But refresh my memory.
Sure. So Bell found a way to test whether the universe is truly local, meaning only influenced by its immediate surroundings.
Okay.
And Clauser's experiment was the first to confirm Bell's theorem.
So it actually happened?
It did. It turns out the universe isn't local after all. Things can be linked beyond their immediate surroundings.
Wow, so it's not just that we can't explain it. It's that the universe fundamentally operates in a way we didn't expect.
Right, exactly.
That's huge.
It is huge. It really is.
But if we can't send messages faster than light with this, what good is it?
Ah, but that's where it gets exciting. While we might not be sending messages like telegrams through entanglement, the implications are revolutionary.
Okay, like what? Give me an example.
Think of it like this. Entanglement could be the key to unbreakable codes, teleporting information, even talking across the vastness of space.
That's where things start to sound like science fiction.
It does. But the line is blurring.
Okay.
China's Micius satellite. It's already using entanglement for secure communication across thousands of kilometers.
So this is real.
We're talking real-world application here, not just theory.
So entanglement is less about sending secret messages faster than light, and more about changing the very way we communicate.
Precisely. It's a fundamental shift. And there's a crucial concept to understand here, the no-cloning theorem.
Okay.
You can't just copy a quantum state.
Oh, okay.
It's like trying to photocopy a snowflake. The moment you try to capture it, it vanishes.
So even though we have this spooky connection, we can't just control it to send whatever we want.
Exactly. We can't control the outcomes of quantum measurements. They're inherently random.
Oh, so it's like...
It's like flipping a coin. You know it'll land on heads or tails, but you can't choose which.
Right.
That randomness, that's both the beauty and the challenge of entanglement.
So are we stuck?
Whoa.
Even if entanglement is faster than light, does this mean we can't actually use it for communication?
Not quite. Not quite. Scientists have measured the speed of interaction between entangled particles.
Oh, no.
And guess what? It's indeed faster than light.
Wait, didn't we just say nothing can travel faster than light? Are we breaking the laws of physics here?
It is fascinating, isn't it?
Hmm.
While the interaction is faster than light, it doesn't break causality. We still can't send usable information faster than light using this phenomenon.
Okay, that's a relief. So we're not rewriting physics textbooks just yet?
No.
But if we can't send information faster than light, why are we even talking about entanglement and communication?
Because entanglement isn't about sending data like we do with radio waves. It's about creating a connection, a channel that's instantaneous regardless of distance.
Okay.
Think of it as a bridge across space itself. We can use that bridge to send information via traditional methods, but with far greater security and efficiency.
So it's less about breaking the speed limit and more about finding a shortcut.
Exactly.
That's incredible.
It is.
And that leads us back to NASA and their work with entanglement.
Ah, NASA. They're always pushing the boundaries of what's possible. Imagine a future where we can use entanglement to communicate with spacecraft, exploring other star systems. We're talking real-time control, high-definition images, and video. From distant probes, a whole new era of space exploration. It's a tantalizing prospect, isn't it? Communicating with distant spacecraft as easily as we talk to someone across the room, but to understand how that might be possible, we have to delve deeper into the mysteries of entanglement. It's not just about distance, it's also about challenging our very concept of time.
That's what's really got me hooked. Does entanglement mean time isn't what we think it is? Is this where we start talking about time travel?
Time travel is a bit further down the rabbit hole. But entanglement does make us question our everyday understanding of time. Imagine this. What if the entangled particles aren't sending signals back and forth? What if they're actually part of a single unified system, outside of our normal perception of time?
So instead of two separate particles communicating across space, it's more like two sides of the same coin, just existing in different parts of space-time.
That's one way to think about it. And if that's true, our linear understanding of time, with its past, present, and future, might be incomplete. At least at the quantum level. It opens up the possibility that entanglement isn't bound by the same temporal rules we are.
Okay, that's a lot to process. It's incredible to think we're only just beginning to scratch the surface of these fundamental concepts, but before we get lost in the theoretical weeds, I want to bring it back to the practical side. What are some of the real-world applications scientists are working on right now?
Well, we already mentioned China's Micius satellite, which is using entanglement to create unbreakable codes. This isn't just a theoretical exercise, it's a working example of how entanglement is changing the way we communicate. It's like having an invisible, impenetrable shield around your data.
That sounds like something straight out of a spy movie.
Yeah.
And what about quantum computers? Are those still just a futuristic dream? Or are we getting closer to building them?
Quantum computing is another area where entanglement is playing a key role. While it's still early days, companies like Google, IBM, and Microsoft are making remarkable progress. We're talking about computers that could solve problems in seconds that would take classical computers millions of years.
That's mind-blowing. What kind of problems could these quantum computers solve that are so far beyond our current capabilities?
Everything from designing life-saving drugs to modeling complex climate patterns to breaking the encryption codes that protect our online data. The potential impact of quantum computing is truly transformative.
It sounds like entanglement isn't just a scientific curiosity. It's a key that could unlock solutions to some of humanity's biggest challenges.
Precisely. And it's not just computing and communication. Entanglement is also revolutionizing fields like medicine and material science.
Hold on, medicine. How can something as abstract as entanglement impact healthcare?
One area is quantum imaging. Imagine medical scans that are so sensitive they can detect diseases at their earliest stages, long before any symptoms appear. Or non-invasive procedures that can pinpoint and treat diseases with pinpoint accuracy, minimizing damage to healthy tissue.
That sounds incredible. Are there any specific examples of how this is being used?
Researchers are already experimenting with using entangled photons to create images of biological tissues with detail never before seen. This could lead to revolutionary new diagnostic tools for a wide range of conditions, from cancer to Alzheimer's disease.
So entanglement could literally help us see inside the human body in ways we never thought possible.
It's not just about seeing, it's also about treating. Researchers are also exploring how entanglement could be used for targeted drug delivery. Imagine tiny entangled particles delivering medication directly to diseased cells, minimizing side effects and maximizing effectiveness.
That sounds like entanglement could completely transform the way we approach healthcare, making it more personalized. More effective.
And less invasive.
Right.
Absolutely. And these are just a few examples. The potential applications of entanglement in medicine are vast and still being discovered.
This is all so exciting. But let's not forget about space exploration. You mentioned earlier that entanglement could revolutionize how we communicate with spacecraft in deep space. Can you tell us more about that?
Of course. One of the biggest challenges of deep space communication is the vast distances involved. It takes a long time for signals to travel between Earth and distant probes, which makes it difficult to control them in real time. But entanglement offers a way to overcome this limitation.
But haven't we been saying all along that you can't actually send information faster than light with entanglement?
That's right. However, while we can't send data faster than light, we can use entanglement to create a connection that's instantaneous regardless of distance. Imagine having a dedicated, unbreakable hotline between Earth and a spacecraft millions of miles away. We can then use that connection to send information via traditional means, but with far greater security and efficiency.
So instead of trying to send data faster than light, we're using entanglement to build a secure, high-speed bridge across space.
Exactly. It's like having a fiber optic cable stretching across the solar system, but without the need for a physical cable.
Now we're really talking science fiction. I can imagine controlling rovers on Mars in real time, receiving high-definition images from probes exploring Jupiter's moons, all thanks to this entangled connection.
It's a future full of possibilities. And who knows? Maybe one day entanglement will allow us to achieve things we can barely even dream of today, like teleporting physical objects, or even traveling through wormholes.
Okay, now you're really stretching my imagination. But that's the thing about entanglement. It constantly challenges us to rethink what's possible. It's almost as if it's inviting us to explore the universe in a completely new way.
That's a beautiful way to put it. Entanglement isn't just a scientific concept. It's a gateway to a deeper understanding of the universe and our place within it.
I couldn't agree more. But I think my brain needs a moment to catch up with all these mind-bending possibilities.
I understand. It's a lot to process. But hopefully, this deep dive has given you a glimpse into the awe-inspiring potential of entanglement. It's a field that's constantly evolving, full of surprises, and ultimately, it's about pushing the boundaries of human knowledge.
I'm feeling a bit more grounded after that whirlwind tour of entanglement's potential. It's amazing to think something so strange could have such a profound impact on our world.
It really does. It really highlights how the universe operates in ways we never anticipated. Entanglement, it challenges our assumptions and forces us to consider entirely new possibilities.
You mentioned earlier that entanglement might even change our understanding of time itself. What did you mean by that?
Well, if we accept that the interaction between entangled particles is indeed faster than light, it begs the question of whether time is as straightforward as we perceive it. Some physicists even propose that space-time itself might be woven from entangled quantum particles.
That's a pretty mind-blowing concept. Are you saying the seemingly empty space around us, even the flow of time, could be the result of countless entangled particles interacting in ways we can't even grasp?
It's a fascinating, admittedly, very complex idea, but it speaks to how entanglement is pushing the boundaries of our understanding. It's forcing us to reconsider our most fundamental concepts, like space, time, and even the nature of reality itself. And the truly exciting part is that we're only beginning to understand entanglement's potential. As our knowledge grows, so too will its impact on countless aspects of our world.
This deep dive has been a wild ride. We've gone from the theoretical foundations of entanglement to its potential to transform communication, space exploration, and even healthcare.
It really is quite remarkable. It's a testament to how science can challenge our assumptions and open our minds to new possibilities.
Exactly. And I think the most important takeaway for our listeners is that the universe is full of mysteries, and our understanding of it is always evolving. Entanglement is a perfect example of that. It reminds us to stay curious, to question everything, and to embrace the wonder of the unknown.
Beautifully said. What seems strange and spooky today might become commonplace tomorrow as we unlock the full potential of entanglement. So keep exploring, keep questioning, and never stop being amazed by the universe and its infinite possibilities.
Thanks for joining us on this deep dive into the fascinating world of quantum entanglement. Until next time, keep diving deep.